All right, so in this final lecture of the semester, I'm going to finish up talking about biological network analysis by talking about random walks on graphs. But before we start on random walks on graphs, I want to reiterate the K-core algorithm and the definition of K-core because this is what you will be implementing in your final assignment. Although the overall complexity of this algorithm on this slide, so you will be basically implementing the algorithm on this slide, which is very simple. May not be that simple to implement. You may think about how you're going to do certain things, but it's still not that difficult. So I implemented the solution in about an hour or in 1 hour or so. And although the worst case complexity is O(n) cube, in our graphs, in the test graphs that I gave, it works really fast. I implemented by using Java. Even in Java, it was like less than a second to print out all the results. So it was really, worst case complexity is not observed most of the time because at every iteration, the graph is getting smaller and smaller. Less than, if your graph contains very low degree nodes, it gets smaller very quickly, and then you get the final result in less than a second. Okay, so the idea is like this. I will also show that in an example. So we first start with k is equal to 1. We don't have any 0 degree nodes. Since we are given an edge list, for an undirected graph, every node is at least a member of one core. A node with a degree 1 will be a member of at most 1 core. So therefore, it cannot be 2 core. When you increase k to 2, those nodes from the graph should be removed. You may not necessarily remove them they should be removed from the graph. So because they cannot be a member of a 2 core. But while you're removing it, this removal process this removal process should be in a loop, because the first time you remove degree 1 nodes, it may be something like this. Let me show you here. This node that we see here, although its neighbor may be connected to, so it may be connected to a dense part of the graph, okay? But let's focus on this node P. Although it has its degree is more than 1, it still cannot be a member of more than 1 core, because if you look at its immediate neighbors, these, okay, initially its degree is 1, 2, 3, 4, 5, 6, 7. So it has a degree of 7. It could be a member of at most 7 core, you may think. But since it's these neighbors, its degree is 1, so it's going to be removed as in the first iteration when k is 1. This cannot be more than 1 core. So this is, I'm going to attach to it, you can be a member of at most 1 core. I remove this one and say, you can be at most a member of 1 core. The same with the others. So each time I remove them from the graph, what you see here is that the degree of P also decreases every time these are removed, okay? Because they can be at most a member of 1 core and this member of 1 core. And at this point, as you can see, P has a degree 1 left. So P in the first place, although it had initially a degree of 7, it could never be a member of more than 1 core either, because as I keep removing these nodes in the second iteration, actually in the second iteration of the while loop where I remove all those 1 degree nodes, its degree also reduces to 1 because of this single edge. So it has to be removed as well, saying that you can be at most a member of 1 core. Okay, so this loop that we have to continue, so this one here that says we have to continue removing degree nodes with degree k until all remaining vertices are connected to each other by degree k or more. So there is another loop that is going on here for a specific k. So it goes on like this. Let me actually, I can write it here, the pseudocode. So while there are, for example, we can actually do it like this. While still left, we can have a flag that says still left. All right, this still left may be 1 initially. Okay, and as soon as I enter this while loop, I can say still left is equal to 0 or false. Okay, while there are still nodes to left to remove, while you still remove nodes, you have another while loop here. While go over all the vertices in your graph, if a vertex P has a degree k or less, if its degree is less than or equal to k, okay, for this current k, for example, we start k with 1, what we will do is, and there's another loop actually that is outside this. There's another loop here while there are some proteins in there are some nodes in the graph, and you start k is equal to 1 here, and in this outside loop, this is the place where you increment k at every iteration. Okay, so this loop that I show here is for a specific k. Okay, for example, for k is equal to 1. So for k is equal to 1, what I will do is for all nodes in the network, if their degree is less than or equal to k, I'm going to remove them from the network, and I will say still left is equal to true at this point. If you remove any node within this small while loop, it means that potentially some other nodes may have now a less degree because their neighbors have been removed in this iteration. So in this single while loop, I just remove all the nodes with degree 1 or less. So, okay, or actually I can just, instead of having less than or equal, I can just say equal to k, because the ones that are smaller than k are already removed. Or actually making less than or equal to k makes it more safer, because during the removal it may end up being less than k. So here I set still left is equal to 1. So what I do is basically, if you removed any node within this small while loop, innermost while loop, potentially some other nodes are going to have some reduced degrees. For example, in this here you see it had degree 7, but after inside this inner while loop, all its neighbors are gone. This p has degree in this first first iteration, going over all the nodes, this p may not have been removed because its degree was 7. Okay, but after its neighbors are removed, I say still left is equal to 1. There may be nodes still left here to remove, and in the second iteration of this outer while loop, in which, since I said still left is equal to 1 after I removed one node, removing even a single node here makes it potentially possible to remove another node in the next iteration. So as long as there are nodes with degree k or less, you keep removing nodes from the graph. But at this point, when you say still left is equal to 0, and in this while loop, if no node in the network has k or less degree, it means that all of them are going to have degree more than current k. So you are now ready to increment k. You can now exit this while loop. If no nodes are removed here, still left will be still 0, and this loop, you will then exit this loop saying that I have found all the nodes with k is equal to 1. They can be at most a member of one core. Now I'm ready to move on to the next k. You can increment this k outside this while loop and go again, start from scratch. Now for k is equal to 2, you will now need to remove all the nodes with degree 2. Then as long as you keep removing nodes with degree 2, you you keep removing them. You in the outside this while loop, you look for nodes with degree 2 until no nodes with degree 2 have remained in your graph. And at that point, all the nodes in the graph will be 3 or more degrees, which means that they can be a member of 3 core. So that's the idea of this. So and this algorithm is just a textual description of what I have written here. So this one is like a pseudocode of what you will be doing. But so it's really pseudocode. How you're going to implement those, how you're going to remove them from your graph, it's really important. So when you remove, for example, when you remove a node from the graph, you have to make sure that it's removed, not only its row, you just don't delete it from the, you consider the adjacency list. This node has an adjacency list. If you want to remove this node from the graph, just removing its row from the main adjacency list is not sufficient, right? What you need to do is, it has a neighbor list. For example, it's connected to QRS. What do you need to do? You need to go to the adjacency list of Q and remove P from there too, okay? Which will in turn decrease the degree of Q. You have to be, when the removal of a node P affect its neighbor's degree. When you remove this node here, this degree should drop to 1. It should be decreased 1. Okay, so you have to do it for all of its neighbors. Go to the neighbor list of all this. I mean, it doesn't mean that Q is removed from the graph. It just means that Q is just lost one neighbor, so its degree has been reduced. So one hint that I can tell you is that it will be more efficient to keep track of the degrees of these nodes in a separate array in which you can decrease the degree. You may compute the degrees of all the nodes in your graph initially, and each time you remove these, you remove them from the network, but you also update the degree array immediately if you keep a separate degree information someplace else. Okay, so that's a big hint on how you can implement this thing. So you keep doing this until no nodes are left in the graph, and in the assignment your goal is to just print out how many nodes are there in the graph for each value of k. For example, for each node, we will have this value. What is the maximum core that it can belong to? This is what we compute at this point. For each node, the maximum k core that it belongs to has this value of k. So your output will be for each value of k. For example, how many nodes in the graph are members of at most 1 cores? Okay, there are maybe 500 nodes. How many of them may belong to maximum of 2 core? These are mutually exclusive lists. Okay, for example, k core 2 does not include k core 1. Actually, it can be a member. Any node with k core 2 may be a member of k core 1, but the assignment is asking what is the maximum k core they can belong to. So if a node belongs to a maximum of 2 core, it's not a member of a maximum of 1 core. Okay, these are mutually exclusive lists, so you can check whether your output is correct by summing. The summation of all these numbers should give you the initial number of nodes, vertices in your graph. And you are going to continue this until the maximum value of k that can be attained in your graph. Okay, so that's basically your assignment, and the due date is July 13th or 14th, something like that. I think it's like Tuesday or Wednesday after the final exams finish. All right, any question about the assignment or the k-core algorithm? Okay, I hope it's clear. And the M-code algorithm, I mentioned briefly at the end of the last lecture. The M-code clustering algorithm works like this. It finds the k-core for every node, the maximum k-core every node can be a member of. It computes the core clustering coefficient for every node as well. And it defines this measure called core clustering coefficient, which is a multiplication of this maximum value of k with the clustering coefficient, which is between 0 and 1. So it basically, if it's a member of a higher core, Even if its clustering coefficient is 0.8, it may get a larger value compared to a clustering coefficient of 1, which is just connected to two neighbors. All right, so for example, if I'm going to compute k-core for each node in this example, first I remove the ones with 0 degree. In your input graphs in the assignment, there will not be any 0 degree singleton nodes. So this one is removed. That's the only one that is removed. There is no 0 degree nodes left, so I move on to the next k. K is equal to 1. So when I remove this one, I decrease the degree of this from 4 to 3. I remove this one, this one. These are the ones with degree 1. So after I remove all these four of them, with degree 1, the remaining ones are at least degree 2. For example, this is a degree 2, this is a degree 2 one. So I just, when I get to the second while loop, that still removes, or what did I call it? Still left will be 0. There will no node will be removed at that iteration, and then I will make k is equal to 2. At k is equal to 2, all these are removed, which means that they can be a maximum member of a maximum 2 core. And this one too, it has a degree 2. This one has a degree 3. Okay, you see this is a degree 3, but after this node is removed, its degree also reduces to 2. Okay, in the first one with k is equal to 2, in the first run, this one, these are removed. So this one is also 2 right now, because these two neighbors were removed when with k is equal to 1. So this one is removed in the first run of k is equal to 2. This one is not removed because it had 3 in the first run. And also this is removed in the first run. But that's it. Those are the only nodes that are removed in the first run. But still left, since we mark still left to be 1, since we removed these, we make a second run to ask whether after this first run of removal of nodes, are there now nodes with degree reduced to 2? And indeed there are. So this one is also removed because it has now degree reduced to these two edges. Since k is equal to 2, it cannot be a member of more than 2 core. This is removed as well at k is equal to 2. And this one too is removed when k is equal to 2. And you see this, those are the only 2 nodes. And there will, if I go to the third time, there will not be any nodes remaining with k is equal to 2. That's where I quit the inner while loop and I make k is equal to 3. Okay, so this gray ones that are in between, as you can see, they are the member of 2 core. And then this will be at k is equal to 3. There are some nodes in the first run. Let me change the color. In the first one, this one is removed because it has degree, no, it's actually, yeah, it says degree 3 because only these two. This was removed in the previous iteration. So these are the ones that are removed in the first run with k is equal to 3. This is k is equal to 3. This is not removed in the first run because it has 1, 2, 3, 4 in degree in the first run. This one is removed in the first run, removed in the first run, removed. This one is not removed either. So these pink ones are the ones that are removed in the first run of k is equal to 3. But after they're removed, the other ones, as you can see now, has reduced degree. Their degrees are reduced to even to 1 actually. So that's why we need to have, while we are removing the nodes, I just made it full size, so full screen. So here, instead of equal to k, it's the correct implementation should have degree less than or equal to k. Because at some point, when we're at k is equal to 3, some nodes may have, in the second run, they may have their degrees even less than k, as these two with just 1 degree. But they are still a member of k because the ones that were removed when k is equal to 3 were the ones that are member of a 3 core. So they may also be member of 3 cores. So this is how it works. And the M-code algorithm as I said, it computes this k-core core clustering coefficient for every node, and it works like this. It starts with the highest core clustering coefficient node in the network, and then it uses this as a seed node. It looks at its neighbors, and among its neighbors, if, for example, if the k-core clustering coefficient value of this was C, okay, uh, among its neighbors, if there are nodes, for example, which have their C values, for example, for a neighbor, if its core clustering coefficient is larger than or equal to 90% of this largest core clustering coefficient value, these such neighbors are added to the cluster that we are growing. So if it had a neighbor with core clustering coefficient a very small number, less than this 90% of C, but by the way, this 90% or 80% is a parameter of the algorithm that you can set. So its neighbors, which also think that they are in a dense neighborhood, are added to the cluster. Some of its neighbors may not be added to the cluster. So it's not, when we are growing a cluster around this seed node, we don't add all its neighbors to the cluster. We only add neighbors who have core clustering coefficient within some percentage of the core clustering coefficient of this node. And we will continue doing this for the added neighbors too. So for the added neighbors, their neighbors can also be added to this cluster that we try to identify if their neighbors have also a core clustering coefficient. Their neighbors also has a core clustering coefficient, maybe 90% of the original largest one. Okay, you may check the algorithm whether it's 90% of this one or this one to see whether that's the case. But the main idea is that we grow a cluster around the seed node by including nodes which are within certain percentage of the core clustering coefficient of the seed node. So that's the M-code algorithm. Now, if you don't have any questions, we may move on to the random walks on graphs, which we can use the random walks on graph to find relationships between nodes in a network. And I will just focus on one particular application, which is, here, imagine we have a set of nodes, which are some candidate genes we have identified. For example, we have identified these 5 genes to be phosphorylated after some experimentation. In a certain condition, these 5 genes are phosphorylated. Now, our goal may be which other genes in the network may be most closely related, most strongly connected, or most tightly connected to these group of 5 genes. So one thing you can do is, okay, you may say, you may just count the number of connections we have to these 5, but this will just make use of the local neighborhood. Maybe the connection is stronger through some other secondary nodes. It may be the case that, for example, imagine there may be a single node here which is not even connected to them. For example, imagine all of them are directly connected, immediate neighbors that are around here. But this blue one, okay, has no direct connection to that. But each one of them, even this one, is just connected to one of them. Okay, out of this 5, they are connected to all one. Okay, if you just look at the local neighborhood, these are the ones that you're going to probably add and decide them they are really tightly connected to those. But what if we have something like this? What if we have a node which is not directly connected to them, but through another node? Actually, in that case, maybe there should be another one, which is also connected like this. We have another node which is connected to all of them. Okay, so this node that is connected to all of them should indeed be included in our final result, but the other ones are going to come next. This one is not going to be even mentioned in the local neighborhood because it's not directly connected to this one. But what if this blue one is connected to this one with a really strong, high confident link? So would you prefer this one over the others? I would probably prefer this one over the others because this one is connected to a lot of them through it's in second neighborhood. It's not immediately connected, but it's connected through these five through via a strong connection. So random walk sum graphs reveal such kind of secondary topologically strong relationships between nodes in the graph. And the idea, the algorithm is very related to Google's PageRank. Uh, and there are different uses of these random walks and graphs. The one that I described, the application that I described here, is called random walks with restarts. Okay, random walks with restarts, random walks with restarts, in which we focus our attention to a given set of nodes and how close other nodes in the network are closer to them. If we don't have such a focused set of genes, random walk sum graph can also be used to find the importance of the genes in the nodes in the graph overall. And Google actually used the Google's PageRank algorithm uses it in that regard. So I will directly go to the one which without restarts may be a little bit confusing first, but here the way Google's PageRank is computed is to simulate a Markov chain actually. If you have taken statistics, probability and statistics course, you know what a Markov chain is. So every time, we start at some state distribution. We have states which shows where we are currently on a graph. And at every time step, imagine we are moving to another node based on the edges this node has. So we jump to one of its neighbors. So Google actually used this to compute the quality or the importance of a web page. The idea was if a web page has a lot of links coming to it, it should be an important page. So let's compute that. But if we just count the number of links directly, this is a misleading. It can be cheated easily by having a web page that you want to promote and putting lots of bogus links from some unimportant websites. So they also, therefore, instead of directly counting the in degree, Google decided to have, what about the quality of those links? In other words, if the link, are those links coming from important web pages or not? If the link is coming to you from an important page, then the link should be counted larger. Okay, if it's coming from a non-important with no important weight, we shouldn't count that link at all. But this brings us to the chicken egg problem. When you're trying to compute the importance of a web page, how do you know the importance of the others? I mean, if you're going to count that link coming towards you, how do you know the importance of the other web pages that are linking to you in the first place? So it's a recursive definition. Okay, but this recursive definition could be computed by a simulation of a Markov process. This is the random walk is done like this. Initially, our state distribution is we can be any one of the nodes initially. Imagine at each step, we go to another node or another web page if it's a web surfer with some randomly chosen web page with probability, with a certain probability, or we go to one of its neighbors, okay? In order to not get stuck in some kind of an island in this random walk, we just make our random surfer to make certain jumps arbitrarily with certain probability, okay? With probability, this can be decided. This is again a parameter of the algorithm. It could be 0.3, 0.4, but different result, the values of D should probably give similar results. But here, the importance of a web page is defined as the fraction of steps the surfer stands at p in the limit, which means that if you continue the surfing a lot many time steps, the ratio of the page that is visited during this simulation is proportional to its importance, because more important pages are going to be visited a lot by, since they're linked by other nodes, so they're going to be visited. Therefore, this is how this simulation uses. Now, the ones with restarts is that instead of the only difference is that, let me show you the difference with restarts is that when we are jumping to a randomly chosen web page with probability d, if the randomly chosen web page is not all the web pages or is not all the nodes in your graph, but a few select nodes in the graph, like those 5, if you're interested in 5 genes, and instead of jumping to any arbitrary protein, if you jump to one of those 5 proteins that you're interested in, then that means it's a random walks with 3 stars. Okay, so here, consider we are walking, we have a random surfer that is walking on this graph at every time tick. But so this probability C is the same probability with this D, okay? So this D and C are the same thing. So instead of jumping arbitrarily to any one of those nodes, if it's a specific node that we jump with probability C or D, that's the same very thing that for the same purpose. If you're jumping to S with some probability, it means that we are going to have our surfing starting from S with certain probability at every time step. So that's what we call random walk with restarts. Yeah, I'm going to show you how we compute that in an example quickly. Okay, so this is our simulation basically computes this equation iteratively over and over again. With these are just the adjacency matrices that we so P here is the steady state distribution vector initially that we define, and this is the row normalized adjacency matrix, which we turn them into our transition probabilities from node to node. Okay, what I'm trying to say is that if you're at a node here at some time step t, it's a Markov chain. I told you it's a Markov chain. If even because if at time t, okay, I'm at this node p. Forget about the restarts first. If these are the only 4 neighbors p has, and if at time t plus 1, I'm going to be moving to some neighboring node, my adjacency matrix has these as 1, 1, 1, right? But turning it into a Markov chain, we have transition from state to state. So this p being at p at time t is some state. Now, which state I'm going to be at t plus 1 will be one of those 4. All right. So all these ones, they are no longer, in order to turn them into transition probabilities. For example, your state at t plus 1. What is the probability that you're going to be, for example, let's call it P1, P2, P3, P4. What is the probability that you're going to be at P1 given that your state at T is, you were at P. Since it has only 4 neighbors, this probability is going to be 0.25, right? If they're equal, if it's equally likely to go to any one of those neighbors, they need to be all 0.25, 0.25, 0.25. So what we first do is, given an adjacency matrix, which is all zeros and ones, okay? So we have this adjacency matrix. We first normalize each row so that the summation of each row is 1. So it becomes a probability distribution over our transitions. So if it has just 2 neighbors, the probability to transition to one of those neighbors will be 1/2, the other one 1/2. if it has, for example, 5 neighbors, let's have another one here, all of them will be 1 over 5 like this with equal probability. So we first row normalizes adjacency matrix. The adjacency matrix then becomes the one-step transition probability matrix. And we will be using that in this equation, that one-step transition probability matrix. We use it since this is a P is a column state distribution matrix. So for example, if we started with a particular node, it will be 1, 0, 0, 0 like this initially. So since this is an n by 1 matrix, we cannot multiply it with n by 1 with n by n like this. It can only be right multiplied. We cannot left multiply it. We can right multiply it. So therefore, what we actually do is we take the transpose of this. The transpose of this matrix still is an m by n matrix, but we multiply it with this. Like this matrix is multiplied with this, and we get at the end an n by 1 new state distribution matrix in the next step. So if we didn't have restarts, random walk without restarts, if we don't have those jumps, this probability C will be 0 in that case. So we don't need this part, and this part will be 1. So we iteratively, so although it's written P on both sides here, this is the state distribution at time t, and this is the state distribution at time t plus 1. So we start with initial distribution P0. This is the S vector is a column vector itself. So S is a vector like this. If you want to do random walks with restarts, S will be a matrix, column vector like this with 5 genes. If you're interested in 5 genes, it will contain, actually, if it contains 5 genes, they all need to be 1 over 5 here. Okay, it has to be also normalized to summation should be equal to 1. But only 5 of those genes will have non-zero values. All the others will be have 0 values. This is what S is. You simply add 2 column vectors at the end to figure out the state distribution. Okay, I think it will be much more clear when I show you an example. So I'm going to skip this one. I will show you this example in which we do everything from scratch, including the adjacency matrix. So imagine we have this network, and where we want to do random walks with restarts, in which N5 and N6 will be our restart nodes. So which means that my S vector is going to be something like this. There are 6 nodes in this graph, so it's all 0, 0, 1, 2, 3, 4. 5, I'm going to have 0.5, and for 6, I'm going to have 0.5. Okay, so this is what the restart vector is going to look like. I'm going to multiply, every time I'm going to multiply it with some constant C with probability. I'm going to scale them so that the state distribution always, the summation of the probabilities in the state distribution always adds up to 1. So actually I have this in the next slide, I think. Yeah, our starting vector, which also I name it my initial state distribution, is like this. This is my adjacency matrix, which shows the connections. For example, N4 is connected to all the other 5 nodes, and I have here 1, 1, 1, 1, 1. I have 5 ones for N4. N1 is connected to N4 and N6 only. As you can see, N1 is connected to N4 and N6. So this is a symmetric adjacency matrix I have here. I normalize this so that the values here this one becomes 0.5, 0.5. This one stays. N2 is connected to only one of them, so its state transition remains still as 1. This N4 becomes 0.2, 0.2, 0.2. I have it here actually. So the second step is I normalize it. And this is my start, and both the restart vector and my initial state distribution. So it's like you start your random surfer at N5 and N6. and your random surfer may equally be likely in one of those nodes with equal probabilities. Where will it be in the next iteration? We find that by running, so let c equal to 0.3. So let our restart probability be equal to 0.3. So what you see here is that equation. At time step 1, I find it by multiplying with 1 minus c 0.7, and this is 0.3. So I multiply this with 0.3. It becomes a column vector 0, 0, 0, 0, 0.15, 0.15. So this is actually fixed. At every iteration, N5 and N6 is going to receive 0.15. So the probability, wherever I am currently actually, since my restarting like teleportation probability is 30%, 15% of that teleportation probability goes to this one and 15% goes to this one. So wherever your random surfer is, with 50% probability to each of these N5 and N6, you're going to find yourself in one of those nodes. But the other, where you're going to be next, is determined solely by your adjacency matrix, your transition probabilities. So we get the transpose of this because the transpose of this tells you, so if you don't take the transpose, this one tells you from which state, where you're going. So since we're going to be multiplying this with this for N1, and I want to figure out at N1 which nodes I'm coming to N1 from, and therefore it should include the first column. The first row here should show actually the first column of the original adjacency matrix. That's why it's the transpose. So for example, you arrive with 0.2 probability, you arrive to N1 from N4, right? N4 had a connection with 0.2 probability. So what we do is we get whatever at the previous stage, whatever probability we were at N4 in the previous time step, we get 0.2 of that, and we to arrive at N1. So the way the multiplication is done, in order to figure out the probability that I'm going to be at N1 in the next time step, I take these values and I multiply each of them with this. So this is how you do the matrix multiplication, and you add up all those. So 0.2 times 0, it's 0. 0.20 times 25 times 0.5, which is 0.125. So N1 is going to have 0.125 actually, and multiply that with 0.7, because this is your, by following the links, you have with 0.7 probability you follow the links. So that 0.125 occurs with 0.7 probability. Okay, so you have to multiply it with that, and what you see here is 0.7 multiplied by 0.125. Okay, and as you can see, N2 is 0. That's because if you multiply N2, the only possible way to come to N2 is via N4, and at time step 0, we were not at being, the probability to be at N4 was 0 at time step 0. So since the only way to come at N2 is via N4, so it's impossible to be at N2 at time step 1, and it is shown here with 0 probability. Now, this is where we are going to be at time point 1. So what we're going to do is, we're going to repeat in random walks with restarts, we're going to repeat this simulation. So this was a simulation of one time step. We are going to continue doing this until steady states, which means that PT becomes equal to PT plus 1. So in the next simulation, what I will do is I will have this P1 inserted in place of P0 and rerun the same equations, this time with P1 to compute P2. Then I will insert P2 here to find P3. And if I do it in a while loop to compute P4, P5, P6, at some iteration, okay, so here's how P2 is computed. Oh, and there's a typo here. If this is P2, this should be P3, right? Yeah, I inserted P1 here to compute P2. Oh, actually, no, this is P2 still. So this is the computed values of P2. Okay. Now I'm going to insert P2 here to compute P3. And if you continue doing this, you're going to see that at P21 and P22 are going to be, if you're just using, for example, 3 digits after the decimal point, P1 and P2 are going to have the exact same 3 digits after the decimal point. And it will keep on like this. It will arrive at steady state, and this will tell us basically, for example, if you're looking for the closest nodes that are most tightly connected to N5 and N6, you see, we have to look at the other remaining 4 because our goal was to figure out which protein in this network is most strongly connected to these starting nodes. Okay, is it N1? Is it N3? And it turns out to be the top highly connected one turns out to be N4 with 0.2 affinity. The following one, N1 and N3, since they, as you can see, they are connected to these with the same topology, they have the exact same equal affinity to those. So if I were to sort them, if I were to add them to this set of genes as another, the next gene to be analyzed or experimented with, N4 would be at the top of my list. N4, then N1 and N3 equally weighted, and then N2 comes. So this is how you would do random walk with restarts. Okay, random walk without restarts just ignores this part. Okay, or random walks without restart, C is just equal to 0. Okay, if C is equal to 0, it will not matter where you started from, it will converge to some steady state independent of what P0 is. Okay, so that's something interesting. If you have a connected graph, regardless of how you initialize P0, it will not matter actually. Random walks without restarts. Okay, random walk without restarts is the application of this algorithm in which C, that jumping teleportation probability is set to 0. In that case, this part is going to be 1.0. It becomes your regular Markov chain. All right, so this concludes my discussion on random walks on graphs. Okay, so I will be happy to answer any questions if you have any. And this concludes all the topics you're supposed to cover in this semester. We are going to have the final exam on Tuesday at 1:30, and its format is going to be very similar to the midterm exam. Some questions may be randomized, some questions not. There will be small short answer questions. There may be numerical questions in which you may have to do computations like these. You will be free to use calculators or any sources that are available to you on the web. And that's it. If you don't have any questions, if you plan to have a question, please type yes quickly in the chat box. If not, I will stop annotation and I will stop recording at this point.